Hello guys, welcome to Nerdsup. Today I'm gonna demo you gradient descent. Yeah, guys, we're gonna code gradient descent from scratch. All right, but before we get started, I would like if you have not seen my previous video on gradient descent, then go check out my previous video and then come back. All right, so let's get started. All right, so this is our data file data.txt. This is how it looks like. We have a bunch of points and we want to find the best fit line for this points. So this is our training data, and x value is separated from y value with a space. All right, so this is the data.txt file. So let's get started. Let's import our dependency. We are going to import numpy to make our life easier. We're going to import matplotlib for which will help us in visualization. So, and we're going to import math for math operation, and finally we're going to import matplotlib inline, the magic function. All right, so let's run this. Great, no error. And now we're going to store the data.txt, the file name, in a variable called file. So let's store it, data.txt. Okay, and we're going to run our gradient descent for 30 iterations, and our learning rate is going to be 0.0001. all right, so let's define a new function called load data that will take as parameter the file, and it will return us our training data, which will be x points, y points, as well as the heading, which is the first line, x heading and the y heading. So yeah, now let's define this function in the cell. All right, def load data, it takes as parameter file name, and input file, let's open the file with read mode, open file name and art. Okay, and first is equal to true for the first line. All right, and now x data, we're gonna define two lists where we'll store the x values and the y values or training data, and we're gonna iterate through each and every line of the file. So for line in input file, yeah, for line in input file, and we're going to write an if statement. If it's a first line, then we're going to store the line dot split values in x head and y head. So x head y head equal to line dot split, and then first is equals to false, because then it's the line will be a second line, it won't be a first line anymore. And then x value and y value equal to line dot split. So now we're going to store the value of x and y in x value and y value, and finally we're going to append those values to the list that we declared above. It should be x value and not x values. Yeah, x value. Yeah, and finally same we're going to do it for y data dot append y value. Okay, and that's it. We're going to return the list x data, y data, and x head and y head. Great, we're gonna run this, no error. We're gonna load the data. So finally our data has been loaded, and now we're gonna visualize the data. So let's write a new function, plot data, that will plot our data for us. So it will take the same parameters that that it returned from load data function, and let's define the plot data function over here, and x label and the y label, and fig equals plt dot figure, and plt dot scatter, let's scatter our points, our x points and the y points, x comma y, and figure equal to fig. And finally we're going to define the label for x-axis, so plt dot x label, and same we are going to define the label for our y-axis, so y label, and finally plt dot show. Now let's run this cell, no error, great. And let's run this cell, visualize our data. Wait, why is the label like that? Oh, we didn't okay, so we didn't convert our x value to float. When we are reading it, it's a string, so we have to convert it to float. So let's convert it to float and run this cell, no error. Let's run this cell, no error, and let's run this cell. Okay. Whew. So finally we have plotted our data. This is how our data looks like, and we have to find the best fit line for this data. Okay, so let's run another cell, or let's create another cell, and we're going to define the gradient descent function over here that will do the gradient descent for us, and it will take as parameters the x points and the y points. Okay, let me copy it, let's paste it, and it's going to return us the weights, which will be optimal b and the optimal m, where b is y-intercept and optimal m is the slope. So let's code this function gradient descent, def gradient descent x points y points, and we're going to initialize our weights to 0. Remember, we randomly start with some weights, so we're going to start with 0, and then we're going to iterate through every iterations. We're going to perform this for 30 iterations, and then in this iteration will return us some values of b and m. So step gradient function is going to do that for us. It will take as parameters our weights and our training data, that's x points and y points, and it will return us b and m. For that iteration, the optimal value of b and m will be this, and let's return this value of b and m in a list. Okay, great. Now let's code step gradient function in this cell. So this step gradient function will calculate the error gradient and the update our weights. All right, so p current, m current, and the x values and the y values. Okay, so we'll have two weight gradients, which we call it as b gradient. We'll initialize it to 0, and m gradient, which will also equal to 0, and then we're gonna iterate through each and every data point to get the error gradient for that data point, and then we're going to calculate the total error gradient across the whole training data. So let's write a for loop for that, but before that, let's define n, which is total number of data points we have. So that's length of x values, and let's now iterate through each and every data point. So let's write a for loop for that, and x equal to x values of I, and y equal to y values of I. So x and y are the current values in the for loop, and b gradients equal to plus equal to. Before that, let me show you the formula for error gradient with respect to b. This is the formula for error gradient with respect to b, and then this is the error function that we are going to use. It is a mean square error, and this is the error gradient with respect to b for that error function. So let's look at the formula and just code it up. M current into x plus b current. All right, see, it's very easy. You just look into the formula and code it up. All right, so let's do the same for m gradient, and let me copy this and paste it. So the formula for m gradient is this: error gradient with respect to b with respect to m is equals to input into error gradient with respect to b. So let's just multiply it with x, which is our input, and yeah, so then we have to multiply it with minus 2 by n. As you can see in the formula, there's a minus 2 by n, right? We're going to do it same for m gradient, because m gradient also has that minus 2 by n. And finally, we're going to update our weights. So the formula for updating our weights is that new weight equal to old weight minus learning weight into weight gradient. So let's just look into formula and code it up. New b will be equal to b current minus learning rate into b gradient. Yeah. And now same we are going to do it for m. Let me copy it, paste it. Wait, what happened? Let me paste it again. Wait, what's happening? We copy it again, and let me paste it. Okay, finally, new m and m current, and it will be m gradient, and we're gonna return this value of updated weights. That will be our new weights, new b and new m, in a list. And yes, let me run this cell. So, but wait, why the function is 2 times? Oh, I copied and pasted the whole function. Let me delete this. All right, okay, we are good to go. Let me now run this cell, and yeah, no error. Okay, let's move forward. So let's run this cell as well. Okay, great. Let's run this cell. Float object is not callable in step gradient function. I don't know what went wrong over there. Okay, let's debug this. All right, let's debug this. Let me check. Let me check the error again. It said B gradient line 8. Alright. Okay, so we're gonna debug this, what the error is, and we're gonna make it run. Alright, I'm gonna print the values of M current. Actually, I'm gonna print the values of M current into X. Let me just print the value of M current into X, and then I'll print the value of the whole P gradient formula that we have over here. Wait, there's a minus over there, right? Yeah, there's a, oh, we missed the minus over there. Okay, so that's why it was throwing the error. Let me run this again. No error. And run this cell again. And finally, let's run this. Hopefully no error. Yeah, so whew, no error. So we have computed the optimal B and optimal M values for our gradient descent. And great, let's load the data again. Let's scatter our data again to visualize our data, and let's run this. But before that, now I would like to so now what we are going to do is that we're going to visualize that how our gradient descent works for each and every iteration. So we're going to plot the values of B and M. We're going to plot a line based on the values of B and M for every iteration. So let's define a function called plot line, which will take parameters as the weights. Let's think. Yeah, let's weights, heading, and the points, the training points. Okay, so let's give it as parameters the x points and the y point, and the x heading and the y heading, which we'll use as labels, and M and B, which will be our weights. Okay, let's define this function, that plot line, and let's make x points as x and y points as y, and x label and the y label just to be consistent with the function. And let's copy the contents of plot data function. And finally, we now just need 3 lines of code to plot the line. So x values equal to np dot array x, and y values is equal to, so what's the equation of a line? Equation of a line is mx plus b. So let's make this as current m, and let's make this b as current b, and we're going to apply the formula mx plus b. So it will be current b plus current m into our x values. That's our input. All right, and now we're going to find and plot these values, which will give us a line. All right, x values, y values, and yeah, and figure equals fig. Okay, let's run this cell. Oh, I missed the colon over there. Let's put a colon and again run this cell. Okay, great, no error. Wow. And let's visualize it, and boom, wow, you can see the results over here, right? We are converging. Initially initially, so over here finally we got the, so in the last few iterations we see that the line is like a perfectly fit line, right? As you can see, right? So now let me just print the values of the optimal M and optimal B in this cell. So optimal B is equals to optimal B, and optimal M is equals to optimal M, and let's run this cell to get the values of optimal B and optimal M. So optimal B value is 0.3 and optimal M is 1.4. M is our slope, B is our y-intercept. But another thing that I would like to do is that compute error for each and every iterations. So let's define a function for that, compute error function, which will take the values of weights and our training data, that's x points and the y points, and then we're going to print this value for each and every iteration, right? So print error is equal to compute error function, and finally we're going to define this compute error. To define it, I think we'll make a new cell for this. Let's insert a cell below and define the compute error function over here. So compute error and this will be x values, and this will be y values, and total error. Yeah, so we're gonna iterate through each and every data point to calculate the error that it wait. I think I have defined another cell for computing. Yeah, over here we're gonna write the function over here. So we have this total error, right? So we're gonna iterate to each and every data point to compute this total error, so that we get the error across the whole training data and not just one single data point. Okay, so we're gonna write a for loop for that to iterate to each and every data point. So this will be length of x values, and finally x equal to x values of I, which will be our current value of x, and y value is equals to y equal to y values of I, and we're going to compute the total error, which will be this formula over here that I have highlighted. This is the mean square error function formula, guys. So we just take a look into the formula, and let me code this up. So it's y minus m into x plus b the whole square. Okay, great. So we have computed out our error, and we're gonna return the total error, but we're gonna divide it by 1 by n. So that's why that you can see the 1 by n in the formula that we have. Yeah, that's the 1 by n in the formula. So we're gonna return this. We're gonna run this cell, no error, and we're gonna run this cell, no error. Great. So let me just print out for error for each iteration. So it's going to be error for iteration I. Okay, let's run this cell. Let's load our data again, and let's visualize our data, and finally let's perform gradient descent for 30 iterations, and boom, you can see the results. So initially the error for iteration 3 is 134, but as for error for iteration 4 is 118. So the error got reduced from 113 to 118, right? So you can see the result for iteration 1 is 457, for iteration 2 199, and then the error gets stabilized, and you get a best fit line, as you can see. So the error gets stabilized at 112.64 for iteration 28 and iteration 29, and finally we get a best fit line. So congratulations, we just did our gradient descent. All right, now I would like to just rerun this cell to see what's the optimal weight. Yeah, it's 0.03, and optimal value of m is 1.47. And so this is the visualization of gradient descent. Okay guys, congratulations, we did gradient descent. We coded up from scratch. All right, this is all for this video, and in the next video we're gonna perform gradient descent. We're gonna do linear regression with scikit-learn package to see to compare our results, how well we did. All right, and guys, if you like this video, if you like our videos, then do subscribe to our channel, and don't forget to hit the like button. All right, see you guys.